So the wish list for such studies would be obviously to to have a set where you actually have good astrometric data, and which could actually help us determine cluster members, because that's very essential when you want to study astrophysical parameters of open clusters, right? And therefore the answer to this problem of ours has come in the form of Gaia, right? So I stopped this presentation. Yeah. So the answer to our problem comes in the form of Gaia. And Gaia is an ESA satellite, which actually gives us this kind of data, right? And so Gaia was actually sent out in space because that actually gives us the ideal advantage of observing from space without having the bending and twinkling effects of the atmosphere, and giving us good astrometry. So that's the satellite Gaia. And And what you see is that you have this excellent data set of astrometric data, where you have excellent astrometric data with precision, right? Now, but the problem with Gaia is obviously that this is a very large data set. And therefore, if we are using this very large data set to study star clusters, there are obviously very big problems because of the amount of positions and the amount of stars that you have available. And for this, our solution comes with machine learning. So machine learning is a very effective tool which can help us do object identification, classification. It can help us clean images, make schedules, etc. Right? And therefore, that's exactly what we use with Gaia data, where we can use different kind of learning methods. We can use the supervised or the unsupervised methods, as well as the reinforcement. But today I'll be basically talking about the supervised and the unsupervised methods which we used. So first of all, I'll talk about a paper of ours in which we actually tried to use a supervised technique of actually looking for members for this sample of 9 open clusters. So we took a sample of 9 open clusters which had ages ranging from 1.3 to 20 million years, and a large set of galactocentric distances, and we actually determined members for these. Now, how did we do this? We did it in a supervised method. So we actually used data from this paper, and this paper had, in a very strict manner, defined the members for all the stellar clusters of the galaxy. And we used a set of these 9 clusters, for which we used their data, the member data, as our training set. This was the training set. And then we used random forest to actually define members for our training set. And here I can show you plots of the orange stars are the training set, and the blue stars are the ones we got from our machine learning. So you can obviously see that we increased the number of members by 2 or 3 times. You can see the sizes of our clusters have very well increased from what was the original size of the clusters. And you can see they very well agree with the parallax plots. You can see the orange is the old stars, the blue is the new, and here you have the combined ones, which is exactly what's done over here, the old, the new, and the combined methods. And you can see that here, if we actually do proper motion plots, these are for the old members, these are for the new, and this is the combined. So you can see that now with the combined membership, we can actually see substructure in proper motion space for all these 9 clusters. If we move ahead, even in sky plots, you can see this is the old, the new, and the combined. You can actually see a lot of further substructure within these clusters using the new members. And here are the color magnitude diagrams with the old members and the new members. The old ones are in orange, the new ones are in blue. And you can see that very well in this method, we can identify these are young clusters, and you can identify easily the pre-main sequence stars, which were not very well identified in the earlier sample, which was used in our training set. Now, we used some methods of validation for the training set. The simplest one was we divided our training set in a ratio of 30 to 20, and we tried to check how well could we retrieve the training set data when we ran our simulations. And we did that in quite a good way. So you can actually see we have estimated the precision we have in this, which ranges from 85% to 95% is the precision we get in this method. So the results you can see is that we increase the membership by 2 to 3 times. We improve the accuracy and determination of various parameters. The size are revised, as well as substructure is found. But the problem with this is that in the supervised technique, you have to have a lot of confidence in your training data set. And therefore, the question was that would it run better if we were to do it without a training set, which we use, which is called unsupervised learning. So in unsupervised learning, we do not assume a training set or a data set of members. And how could we do it with that? So we try to check out some unsupervised learning techniques to check whether which of these techniques are better and do they work better on certain cluster types or no. And therefore over here, I'll show you. So the first technique we used was we tried to compare the Gaussian mixture modeling with what we get with DB-scan. DB-scan is the a density-based scattering method, but the Gaussian mixture is another method, which this one has been described in Gao 2018, this one in Agarwal. And so you can see in this paper by Agarwal et al., where they actually use nearest neighbor method and Gaussian mixture modeling to actually determine membership probabilities of individual sources. So we did something similar with our sample of again 9 clusters where we used Gaussian mixture modeling. And this is a paper in preparation where we actually, you can see that the number of members has been increased by a major factor. This is the number of members we get using Gaussian mixture modeling. The only problem with Gaussian mixture modeling B is that we assume a Gaussian distribution of these clusters, right? So if these clusters do not follow a Gaussian mixture, then obviously we will have some problems in our data, right? We also tried this method. This is work in preparation with a set of more clusters with the DB scan method. In the DB scan method, we do not assume a Gaussian mixture. And therefore, here you can more effectively identify cluster members. And in this color magnitude diagram, for the very same clusters, I have compared the color magnitude diagrams which we obtained using random forest, using the training set of contact coordinate, as well as the data we got with our DB scan method, which is mentioned in these 4 color magnitude diagrams over here. Some of this work has been done similarly by other authors also using DB scan method to actually use and define the parameters. So one can use this to actually define the parameters of these clusters to much more precision, essentially their parallax, their proper motions in RA and DEC. And there's a present work which we are actually doing again in preparation, which is with serpents. Serpents is a star forming region. And here, what we have on the left hand side, this is the extinction map where I've shown you the young stellar objects, the YSOs for this star forming region, which we found using various data sources, X ray data, infrared data, etc. We cross-matched this with Gaia data, which is shown over here on a WISE image. And we've actually used DB-scan to actually find members for this star-forming region, with which we can better characterize the parameters for this region. And we are repeating this data using...
2 minutes more.
Yeah, we are repeating this data using clustering algorithms like optics as well as HDB scan, because both of them have advantages of their own. So you can see with serpents, when we ran DB scan and optics, this is the DB scan. This basically gives me the membership data for this central part, which you can see over here, for this central part of the star forming region, which is showing up over here. With these are not very important clusters; they have much smaller membership. And here you can see with optics. In optics, you can actually optimize the value of epsilon, which is used in this, and we can again identify the members. So I'd like to conclude with this, that machine learning members are gaining popularity. They are very useful. And specifically in this problem of membership for star clusters, it proves to be very effective, especially with Gaia data, because you are using a 5-dimensional space data, which is the spatial coordinates as well as parallax and proper motions. And in that, we actually see that we very effectively managed to find out a very good membership data set using Gaia data and various techniques of machine learning, including the supervised as well as the unsupervised. So thanks a lot. I'll end with this. Yeah, thanks.
Thank you very much. Let's end.
And
Ryan?
sorry for the problem. Yeah.
No questions, please.
Yeah, Gabriel.
Okay, Gabriel Terren, please.
Hi, can you hear me?
Yes, I can hear you.
Hi, Priya. Just one small question. Have you tested your methods with other published methods for membership? There's UpMask and the recent PyUpMask by my group. It would be interesting to know how your methods compare to other
Yeah,
already
yeah.
published methods.
Yeah, thanks, Gabriel. So actually, yes, in that plot which I showed you, the contact coordinate methods are anyway with upmask. So we have compared it with upmask. We have not done it with pi upmask, but with upmask we've done it. And we are actually using your code, the Azteca code, to actually determine parameters for our, for these clusters. So we have been
Oh,
in
okay.
touch, right? Because if you remember, we've been sending you quite a few emails, because what we are doing is we are using Azteca so that in a homogeneous way we can get the parameters for our clusters.
Oh,
Yeah,
okay. Okay.
yeah.
Great.
Thanks a lot. Yeah, thanks.
Thank you.